Welcome to the world of chemistry. We want to look particular at how to describe the shape of a molecule based on valence shell electron pair repulsion theory, which makes good use of Lewis structures. So we're talking about VSEPR, valence shell, and that's the outer shell. Electron pairs, we look at the electrons and pairs, bond pairs, lone pairs, repulsion theory. So we start with a kind of an idea that when things repel each other, they get as far apart as they possibly can. And then that makes them orient. If you have two things that repel each other, they're going to get 180 degrees apart. Three things, 120, four things, 109 degrees. But I want to show these angles specifically and how it works. So I thought I would start here with a simple example, and I'm going to use balloons. We're going to imagine that these are electron pairs of some kind, and we're going to just tie these two balloons together, and they are going to, they'll be in each other's space, and so they're going to try to be far apart as they possibly can. So here's this pair. What happens if you do this is they will assume static electricity. They will assume 180 degrees apart. That's as far apart as their space down here forces them into a configuration that's 180 degrees. If I were to draw this on the board, it's not hard to do, but I'm going to say I would put the dot for the central atom, and I would just draw like that, and that is 180 degrees, and there'll be some atom. And that results, if there are atoms here, in a linear configuration, okay? Well, let's do a little more interesting thing and see if we can do the three. At some point in time, I can just add things. Yep. Just add this orange one here to this. So now I've tied three regions of density together, and very nicely I have a shape that I'm going to call all moved about at an angle of 120 degrees. So you have to imagine the central atom here, three regions of density of electrons, okay? And so this kind of shape could be, here's the central atom, here's the atom out here, drawn like this, and this is 120 degrees, okay? And that, if there are atoms present there at the ends, this is called Trigonal Planar. How it gets that name is the three atoms that are peripheral atoms form a triangle, trigonal, and they're in the same plane. The central atom is there too, but we don't count that. It's these three that form a triangle, trigonal planar. Now, there is another shape that could result in this. What if these were not bond pairs? And to say they're not bond pairs would mean that there's no atom at the end. They're just that. So let's say the orange is a lone pair. Then what you would have, out of the same basically three regions of density, you would have something like this. There's the atoms, and then you'd have this pair, which doesn't figure in the molecular geometry. It's arranged in space, and this would be a bent molecule, 120 degrees, because there's the bend. This atom to the central atom there. So there's a little bit of clarification I need to make on this. So the three regions of density is going to assume the 120 degrees apart, but if they're bonded pairs, then you're going to have a trigonal planar molecule. But if it's a lone pair, you're going to have a bent, like in the region of the red, 120 degrees. Okay? Let's just tie together four of these and see what happens. Now, this is where some people lose it in three-dimensional There's a gap in three-dimensional thinking. So one of the first answers is, well, I'm going to get 4 in an area, something like an X, in a plane. But no, that wouldn't be economy of the space that was required. This is the region in space that is the most free, moving farther apart. And this particular region, the 4 regions in space, is the shape of what we call a tetrahedron. A tetrahedron, or a trigonal pyramid. There's a one and one, the same things. So basically, the tetrahedron there's a square tetrahedron and so it has a triangle as a base and an apex up above. So the tetrahedron would be represented in this way. And this is where you have to imagine. You start right here, there's a central atom, you come this way, and this way, and this way. And so this angle in here is 109 degrees. So this is how you represent a tetrahedron on the blackboard. And sometimes people will do things like this. They'll say, okay, this is sticking out, and this is in the same plane, and this is back. So, tetrahedron is just a very, very interesting piece of, so like if you do that, a tetrahedron is actually, if you imagine a cube, the top diagonal corners is there and the bottom diagonal corners is there. So it belongs to the cubic system. But this is what a tetrahedron looks like. This is how you might draw it, okay? So a molecule that has 4 regions of density around it and all bonded pairs is going to be a tetrahedral shaped molecule. Well, what happens in this molecule if we identify, say this blue is a lone pair? Now you notice what's going to happen is that you're going to have this incident. You're going to have all of these here, center atom, this atom, that atom, but here is a lone pair. So we don't describe the shape of this molecule in terms of the lone pair, even though it's forced into that kind of geometry. This is going to be called a trigonal pyramid. And remember, the basic concept of a pyramid is that you have some kind of geometric figure as a base and an apex above it. And that's exactly what we have. We have this triangle is the base of the pyramid, and here's the apex, the central atom. Trigonal pyramid. We also can possibly have an idea that what if we had 2 lone pairs and 2 bond pairs in the regions of 4 regions of density. We would describe the molecule as bent. It would look like this. Bent 109 degrees with its other lone pairs up here. Okay, bent. So that is the story. What we have to get the shape of the molecule, we have to go from the Lewis structure, get the regions of density, and then imagine the pairs repelling themselves into those geometric forms. Needless to say, the tetrahedron is by far, because of the octet rule, you want to have 8 regions of density around the central atom. So those 8 regions of density usually assume directions in space related to a tetrahedron. So now we also then, the very last idea is, what can we do about this? Well, one of the things that we can do about this is we can predict whether a molecule is polar or not on the basis of its shape and the polarity of the bond. And so what I want to do is kind of go through these molecules and identify their shape. That I already have done the Lewis structures for you. Okay, let's start with ammonia. What shape is ammonia? Well, we have a model. We actually know there are 4 regions of density around the nitrogen, 3 bond pairs and a lone pair. Guess what? This is ammonia right here. Doesn't see it? The blue is a lone pair, And so what we have to do is describe ammonia as, here's the nitrogen, here's one hydrogen, here's another hydrogen, and here's that other hydrogen. And this is trigonal pyramid. Okay? And then once seeing the shape, we need to ask ourselves, is this a polar molecule? It is a polar molecule if one of the atoms attract electrons. We're talking about electronegativity. That's in the last part of the chapter. And so you look at nitrogen and hydrogen, and you'll see that nitrogen is the bonds are slightly polar. So we could put vectors on this and say there's a bond, a polarity to that bond. Now, actually, I have the arrows pointing towards the more positive, but these are like vectors. They have a little magnitude, and there's nothing pulling up on it. So the net vector is actually something like that, and that's polar. So if the polarity of the bonds form a vector in the direction of the bonds, and they don't cancel, you have a polar molecule. So ammonia is a polar molecule. Now we do something like carbon tetrachloride. That's my next one. And carbon tetrachloride, I'm sorry, it's a dichloromethane. And if we look at dichloromethane, we know that it just has 4 bond pairs, 4 regions of density. And so this is a perfectly good model of a tetrahedron. But this should be green, because it's a bond pair, not a lone pair. So we have a perfect tetrahedron, and if something happened to them, that's okay. So this is this. So what we're going to do is we're going to put 2 chlorines here and 2 hydrogens here. And then we ask ourselves, this whole molecule is tetrahedral. And is it polar? Well, if you look at the electronegativity chart, you'll know that that chlorine is one draws attractions. So this whole part of this molecule is going to be negative. This whole part then will be kind of correspondingly positive. And so we have a net polarity of the negative chlorines and positives. So it is a polar molecule. Okay. Methane, which would be this, would be the same tetrahedral shape, but it would be nonpolar, because you would have the equal pull of the electronegativity in all 4 directions. Little other. What kind of a shape of molecule is sulfur dioxide? We're looking at sulfur dioxide. Sulfur dioxide is regions of density are 1, 2, 3. A double bond, a single bond, and a lone pair. That would look sort of, here you got 3 regions of density, okay? But one is a lone pair. So let's represent that. Here's the sulfur, and here is one oxygen, and here's another oxygen, and here's that lone pair. To describe this molecule, its shape, though, one would have to say that it is bent 120 degrees. Right there. That's the molecule. Is it polar? Well, we know the oxygen is another very electronegative element. Well, all of those elements way in the upper right-hand corner draw the electrons toward us, so this is going to be kind of negative. And this leaves this kind of positive, and so therefore it is polar. The last one here, carbon dioxide, I just put its Lewis structure up there. Carbon dioxide could most easily be represented by 2 far apart, and I actually did. That's the first one I made, and now I converted it into that. So 180 degrees apart. We're okay on that. So we can see this molecule has two regions of density, and they're spread out 180 degrees. And we look at this molecule and we say it is a linear molecule. Linear. And we ask, is it polar? Well, we have the situation that there's electrons being drawn that way by the oxygen and that way by the oxygen. Equal and opposite cancel each other. It is a non-polar molecule. Okay, so in general, this combination of Lewis structures and valence shell electron should help us to visualize 3 dimensions of chemistry and speak about them. I'm going to I'm going to take a little time and set up and show you how you can tell something's polar or not experimentally. I thought maybe it would be important to take a little demonstration on how we might measure polarity. It's an important property, and one of the things that we can do is that we're going to levy off of the idea of polarity when we talk about solvents, and like dissolves like. Like a polar solvent dissolves a polar solute, and water is a very important polar solvent. But what I'm going to do is I have here 2 barrettes, and a barrette they contain clear liquids. And you know, guess what? I have in one of the barettes I've got water, and the other one I have carbon tetrachloride. And I don't remember which one has that. It's, you know, pretty close to April Fool's Day, so I can make a little joke here. But I'm going to show you my skill is going to be able to test this, and I'll be able to tell you which one of these is carbon tetrachloride, which one is water. First of all, I have the knowledge that water is a polar molecule. It's bent 109 degrees, actually about 104 degrees, and it's a polar molecule. Whereas carbon tetrachloride is like methane. It's a tetrahedral shape, and the polarities of the carbon and chlorine cancel, so it's nonpolar. So we got that. Water, polar, carbon tetrachloride, nonpolar. So what I'm going to do is I'm going to use principle that if the molecule is polar, it will be bent. The stream that flows out of there will be deflected or attracted by a charge, because it's polar, and a charge is a pole. So I'm going to create a charge on this glass rod by rubbing it with a little bit of silk, and I'll try this barrette first. This works because the silk will, you know, take off, and I think it produces a positive charge, whereas fur and ebonite produces a negative. So I should have a positive charge on this glass rod pretty well. So what I'm going to do is I'm going to turn this on, and you see the stream falling, and I'm going to approach that stream with this, and you see the stream bending? So that means that's water. This is water. It's polar. Otherwise it wouldn't bend, it wouldn't be deflected. See, it's attracted to this, bending the stream. Well, just to make sure that we didn't fake you in something like that, let's do the other one, which we think is nonpolar carbon tetrachloride. And of course what you'd predict here is you wouldn't see this bending happening, you just see the stream. So I'm making sure I have my charge here. As I have my charge, I'm going to open the barrette. There begins the flow. I'm approaching this, and guess what? Do you see any deflection in that stream? None whatsoever. Oh, maybe it isn't charged. Well, I go over here. Yes, it is. And so I have now demonstrated a physical property of response, because this is nonpolar, not any deflection by the presence of a charge. Polar, the deflection of the stream.